Hey everybody, Dr. White here with a little coda to section 1.3. I thought I'd give you just a couple more little applications, and the first one is the famous birthday problem. This is loosely based on exercise number 11 in the section. So you'll notice that I'm in RStudio, so if you want to follow along, you should log in. And once you're there, you want to head to the ... common folder, white stuff, Math 331, and this time go to slides, and you'll see Chapter 1, Section 3, Birthday. There is an R Markdown source for these slides, and there's also the slides themselves. And we'll look at the slides themselves. So you click on them. You got two options. One is open the editor, which you don't want to do. You don't want to look at the HTML. You want to view in your web browser. I'm going to move my, can I move my face? Yeah. And what you want to do is you want to view it in the web browser. Okay. So I'll move my face back. Okay. And it'll pop up in a new tab of the same browser. And what you see is it's about the birthday problem. Let me make it smaller. There we go. And so the birthday problem starts off with some simplifying assumptions. Let's just suppose for simplicity that everyone's equally likely to be born on any day of the year. We know that births actually vary seasonally, but let's just make it simple for ourselves here. And let's also suppose there's only 365 days in every year, no February 29th leap year day, okay? Now, the problem is this. Say you got 23 people picked at random from the population and they're gathered in a room. What's the probability that at least two of them share the same birthday? That might appear to be a very small chance. Only 23 people, lots and lots of days, 365 of them. Small chance of two of them matching. But let's check it out. Here's the approach I'm going to take. The probability that at least two of them have the same birthday is 1 minus the probability that all 23 birthdays are different. Now, let's take these people, these 23 people, and let's just line them up in a row and call them person 1, person 2, all the way up to person 23. And then think about the event, all 23 birthdays are different, okay? If you think about it, it's the same as the intersection of the following 22 events. The event that person 2 has a different birthday from person 1 intersected with the event that person 3 has a different birthday from persons 1 and 2, intersected with the event that person 4 has a different birthday from persons 1 through 3, all the way up to the event person 23 has a different birthday from persons 1 through 22. Starting at 2, headed to 23, so that's 22 events intersected together. They make the event that all 23 birthdays are different. So find the probability of intersection, you can use the multiplication rule. And you just get a bunch of like probabilities times conditional probabilities. So when you use multiplication rule to get this probability, you start with the probability that person 2 has a different birthday from person 1. And then your next up is a conditional probability, the probability that person 3 has a different birthday from persons 1 and 2, given that person 1 had a different birthday from person 2. And then the next up is that the probability that person 4 has a different birthday from persons 1 through 3, given that persons 1 through 3 had different birthdays, and so on down to the final probability, final conditional probability that person 23 has a different birthday from persons 1 through 22, given that 1 through 22 different. Okay? So what's that going to look like? Well, for the probability that person 2 has a different birthday than person 1, well, there's only 364 days that person 2 could have to be different from person 1 out of 365 possible days. So that first fraction right here is the first probability. And then the conditional probability that person 3 has a different birthday from persons 1 and 2, given that 1 and 2 are different, Well, given that 1 and 2 are different, they've taken 2 days out of the 365, and so there's only 363 left for person 3 out of the 365 total, so this fraction accounts for that probability. And it goes on like that with the numerator and fraction decreasing by 1 every time until you get down to person number 23. And remember, you need a total of 22 of these fractions. And if you look at the numbers from 364 down to 343, the difference in those numbers is 21, and therefore there's 22 of them. So I've got it right there. Okay, and then that gives us the solution to the birthday problem. The probability that at least 2 of them have the same birthday is 1 minus that product. Okay, so we just have to figure out what that is, because I'm interested. Is this a big or a small probability? This is a time I'd like to actually simplify my answer. So heading away from the slides, I'll just close out this window. Now, I'll keep it open just in case you want to look at it. Head back to RStudio, and why don't we just open up a little script here. File, new file, RScript, and I'll do file, save as, and I don't know, I'll call it maybe birthday, capital R, and I'll save it into my notes. So double click on my notes and say save. And if I go back in my files pane to my home and look into my notes, I should see it there. Yep, there it is. Okay, cool. Now I'll just click to home again. All righty. Head to birthday.r. Let's do this computation. So I need 1 minus, and I've got like the product of all the numbers from 363 to 364 to 343. Was that it? Yeah, that was the numerators. And then I got to divide by all those 365s on the bottom multiplied together, and there's 22 of them. Okay, so I'll divide by 365 raised to the 22 power. Okay, and I'll just run this, and wow, I get about 0.507. So there's actually a little bit more than a 50% chance that at least 2 of the 23 people have the same birthday, which is pretty amazing. But now that we're here, let's see what might happen under other circumstances. Like, what if you had 30 people in the room? What if there were 30 people? Let's see, if there were 30 people, then person number 30 would only have, let's see, the persons 1 through 29 would have taken 29 out of the 365 available days. 365 minus 29 is 336. Okay, and so that would be how many days that last person could have, is 336. So I'd need to put a, I would need to, here, I'll just copy this, copy. And write in a 336. And let me see, 30 people, 29 events this time, so I need to raise to a 29. And 70%. So if you got 30 people in the room, there's over a 70% chance that at least 2 have the same birthday. And if you know a little bit more R programming, you could actually sort of generalize this. You could write a little function that tells you the probability of a match when there's like N people in the room. But I'll leave that to you to think about if you've had CSC 115. Hope you had fun with the birthday problem. See you soon.